Hello, this is John from DMV Software, and this is a quick introduction to Phast. The aim of this tutorial is to make you familiar with the ideas and techniques involved in performing a consequence analysis with Phast, and to give you practice in defining a range of common types of hazardous event. The program is supplied with an example study folder called Phast Example Study, which is used in this chapter to give a quick introduction to the terminology and approaches used in the program. To open the study folder, choose File, Open Example. Go to the Tutorials folder and select the Phast Example Study PSU file. The appearance of the main window changes when the study folder is open. There are many more toolbars and there is a pane with 5 tab sections at the left hand side of the window. The pane is known as the study tree pane, and you work in its various tab sections to set up the input data for the analysis. The study tree pane allows you to organise and edit the input data for your consequence analysis. The pane contains a number of tab sections, each of which covers a different type of input data, and these tab sections are now described. The Models tab section shows the set of available calculations, and you define a given hazardous event that you want to analyse by selecting the most suitable model from the list of 11 models. When you select the model from the list, the program will insert an icon for that model into the Models tab section. The icon represents an instance of that model and will have its own set of values for the input data. You can find any number of instances of a given model in your study folder, each with its own set of input data to represent a particular hazardous event. To insert a model, you cannot place the model icon under the study folder itself, but only under a study or folder. To add a model at a particular point in the structure, select the study or folder, and then select the appropriate model from the Insert menu. You can also insert a model by selecting a model from the Insert cascade at the top right click menu, or by selecting the icon for the model from the toolbar. The Weathers tab section contains a folder named Global Weathers, with 3 definitions of weather conditions. The name of each weather gives the atmospheric stability category and the wind speed that are set for it. The program performs a separate run of the consequence calculations for each separate weather condition, giving a set of results that are specific to that weather. The Weathers tab section also contains a study icon called Example Cases. In the Model tab section, all of the models will have been placed inside the example case study, but you create and use any number of studies in an analysis. In the Parameters tab section, as with the Weather tab section, there is a set of global parameters, and you can also define local parameters that are specific to a given study. If you define a local set of explosion parameters, for example, the values in this set will be used instead of the values for the global explosion parameter during the calculation for the modelling in that study. Green borders to the icon show use of default values. All of the icons in the global parameter folder have green borders. The program uses this border to show that all the parameters under that icon are using the default values that are supplied with the program. If you change the values of any of the parameters, then the green border around the icon will disappear. This allows you to see at a glance what aspects of the analysis are using all default values and which are using change values. The program is supplied with a set of system materials that contains full property data for more than 60 materials. However, the Materials tab section does not show icons for all of these materials, but only for those that have been selected in the input data for the various models in the study folder, or for materials that have been added yourself while working in the Materials tab. The green icon shows a pure material, yellow and red icons show a mixture, and pink icons show a pesticide. The Map tab section allows you to set up map images and geographic data so that you can view regions and features affected by consequence results. The map image is defined by the power station raster image, and you view the image by selecting Map from the View menu. The map window will open in the area to the right of the study tree pane, and you can use the options in the map menu, the right click menu, and the map toolbar to zoom in and out, to move around the map menu, and to control the display of the features of the window, such as the scale bar and the legend. The models are represented by dots on the map. These dots can sometimes be difficult to see and to relate to an individual model, but there are several options that can make this easier. Those include changing the size and colour of the dots, displaying the model names on the map, and pinpointing an individual model. You can change the size and colour of the dots on the map by selecting Map from the Preferences cascade of the Options menu. Move to the Models tab section, change the colour from turquoise to blue and the point size from 7 to 10 and OK the dialog. This makes the dots much easier to see in the power station map. You can also display the model names on the map. If you move to the Models tab section and then select any of the models, select Labels from the View menu. The names of all the models that will be displayed on the map. To hide the names, deselect the Labels option. If there is more than one model at a given location, as with the chlorine models and the butadiene models, then the name will be superimposed on each other and it may be difficult to read, although this may make it clear that there are multiple models at that location. To pinpoint an individual model, if you select a model in the study tree and then select Pinpoint from the View menu, the dot for that model will become centered in the map window and will also be highlighted in turquoise. This allows you to locate a specific model, which is useful if you cannot identify the name for that model on the map. You can close the map window by selecting Close All from the Windows menu. We will now view the input data. Move to the Models tab section and double click on the icon for the model named Chlorine Rupture. The vessel pipe input dialog will open. The dialog contains a large number of input fields organised over 17 tab sections, but many of these fields are relevant only to the advanced modelling option, and you will typically only need to supply a small set of input data when defining a model for use in the analysis. This tutorial does not attempt to describe every item in input data, but the program is supplied with a comprehensive help section. Every input dialog contains a help button at the bottom right. When you click on this button, the online help will appear in a separate window. The help window will be displaying a description of the current tab section, but you can use the link inside the topic and the contents index and search tabs to reach any topic in the help system and gain a full understanding of the way that the input data will be used in the calculations and the appropriate values that you should set for the hazardous events that you want to model. We will now run the calculations and view the results. In the Models tab section, select the example case study and select Models option from the Run menu. The program will process the calculations for each of the 18 models in turn, performing the calculation for each of the 3 global weathers, and showing the progress through the calculations. When the calculations for a given model have been completed for all 3 weathers, the name of that model will change from black to blue, which is the colour coding that the program uses to show that a model has run successfully and has a complete set of results. The calculation will take several minutes to complete depending on the speed of your machine. You do not have to run the calculations for all models and all weathers. If you select a single model or folder, then you can run the calculations just for that model or for that model in that folder. Or you can select Batch Weather Setup from the Run menu to select models across different folders or to select only specific weathers. The selection of weather in the Setup dialog will be used for all calculations, but the selection of models will be used only when you select Batch Run from the Run menu. To view the graphs for the chlorine and butadiene releases, select the vessel or pipe source folder and select the option to view graphs from the View menu. A dialog will appear prompting you to choose the weather condition and results you want to view. If you had selected a single model rather than a folder with multiple models, then the dialog would have check boxes next to the weather instead of radio buttons, and you would be able to compare the results for several weathers for that model. If you choose a single weather in this situation, then the graph will have additional features that are not available when you are viewing results for multiple models or weathers. For this example, select the f1.5 meter per second weather. This is the weather with the most stable conditions and is likely to give the longest dispersion distances. When you click on OK, there will be a pause for a few seconds and then a graph window will open as shown in the space to the right of the study tree pane. The graph window will usually contain many tab sections, each with a different type of graph. The tab sections include for a particular combination of models will depend on the type of the models, on the type of the material, and on the detail of the dispersion and effect behaviour. The chlorine models have graphs for cloud concentration and for toxic effects. Butadiene models have graphs for cloud concentration and for flammable effects such as jet fire, fireball, flash fire and explosion effects. The first graph is of central line concentration. This will be showing the results of the time at which the cloud footprint covers the greatest area, which occurs at different times for each weather. The graph will initially be showing results only for the 4 chlorine models. In the dispersion calculation, the program uses an averaging time that takes into account changes in wind direction over the course of the release to give an average concentration at a given location, and it uses different averaging times for toxic and for flammable materials, reflecting the different timescales that are relevant to each type of release. The concentration graph always displays results calculated with a specific averaging time, which is displayed in the legend for the graph. The default averaging time for this set of results is the toxic averaging time, and the butadiene models were not modelled with that time, so have not displayed the results. To view the concentration results for the butadiene models, you must change the selection of averaging time to display. To do this, select Properties from the right-click menu. And then move to the Averaging Time tab section. If you change to a flammable averaging time, the graph will display the results for the 4 butadiene models only. The user-defined option will also be enabled, which shows that some of the models have a user-defined averaging time, defined in the Location tab section. In fact, all of them have such time defined, and if you select user-defined as the averaging time for the graph will display results for all 8 models. After the 6 tab sections that show the results in your concentration, the next tab section is the map graph, which allows you to view different types of effect zones superimposed on the map. When you first move to the map tab section, the map graph will be displaying cloud footprint results for a concentration of 10,000 ppm for the toxic averaging time, and the only results displayed will be for the chlorine rupture and chlorine liquid leak models. The other chlorine models don't produce this concentration level at the default height at the ground level, so you can see from the sideways view graph. But if you open the plot property dialog, move to the distances tab and set the height to 10 meters, results for the chlorine vapor leak and chlorine relief valve models will also appear on the plot. The footprint concentration results are the default form of results for the map graph, but the events field in the display tab section of the plot property dialog allows you to change to a different form. The list of types of effects will depend on the type of model that are covered by the graph, and will be similar to the range of tab sections in the graph window. If you select Outdoor Toxic Effects, then the radiative toxic field will become enabled, and you can choose between dose, probit and lethality results. If you view the lethality footprint on the map, you will see that the chlorine liquid leak gives the greatest downwind effect distance for lethality. The rupture model produced higher peak concentrations at any given downwind location, but the short duration of the rupture means that the total dose received is lower than for the leak. The map graph initially shows the effect zone with the northerly winds, but you can choose wind direction from the graph menu or the right click menu to change the wind direction. The pool vaporization graph does not show any hazardous effects distances, but the toxic graph and the various fire and explosion graphs all include footprint results of the forms shown on the map. Most of them also include graphs that show the effects affect levels along the cloud centre line as a function of distance downwind. The programme also presents results in the form of a report. If you wish, you can view the reports that cover multiple models, but if you want to compare the report results for different models, it is easier to view separate reports for each model and compare between two reports. To view the report for the butadiene rupture model, select the model and then select Report from the View menu, or from the right-click menu of the toolbar. After a pause of a few seconds, the report window will open to the right of the study tree pane. The report window will probably hide the graph window, but you can use the option in the window menu to move around between the windows. You can have any number of graph windows and report windows open at the same time. Similar to the graph window, the report window will normally contain several types of results presented in different tab sections. A given tab section will present the results for all of the weather conditions that have been processed for the model. For the butadiene rupture model, the first tab section is the input tab section, which lists the input data. The audit tab section gives version details for the program, for parameters and materials, but all of the other tab sections give details of the consequence results that you saw summarised in the graph window. The summary report summarises the maximum downwind distance to different types of effects and gives a direct comparison between the different weather conditions. For the butadiene rupture d5 meters per second, this is the weather that gives the greatest distance, although the difference between the three weathers is small. As shown on page 5 of the report. The discharge report gives details of the discharge modelling and the conditions of the release immediately after expansion to atmospheric pressure, which is the condition used in the start of the dispersion calculations. This report, and all the other results reports, gives the results for each weather in turn. The summary report is the only report which presents a direct comparison between the different weathers. The dispersion report is a report containing a table which describes the location and status of the clouds at a series of time steps during the dispersion. You might refer to this report if you wanted to understand the particular aspects of the dispersion behaviour in greater depth. The commentary report highlights the main events in the course of the dispersion and allows you to easily see if and when different types of behaviour occurred. The average times report is the centerline concentration given in the dispersion and commentary report are all calculated using core average time that is set in the dispersion parameters and then has a default value of 18.75 seconds. The averaging time report gives the centerline concentration a series of steps during the dispersion, calculated using alternative averaging times. For the butadiene rupture model, these alternative times are the flammable averaging time and the user-defined averaging time. In this analysis, both of these times are set to 18.75 seconds. For all the butadiene models, the averaging time reports give the same concentration as the other reports. However, if you review the reports for one of the chlorine models, you would see results for the toxic averaging time, and which has a default value of 600 seconds. The fireball report gives radiation results for a fireball resulting from immediate ignition of the released material. The report gives a description of the fireball flame. Then it gives the dimensions of the elliptical effect zone for up to 5 different radiation levels, where the levels are set in the fireball tab section for the model. And finally, gives the radiation level a series of points downwind from the centerline of the release. The jet fire and pool fire reports have a similar form given the same 3 types of results. For butadiene rupture, the tab for the early explosion report is named Early Explosion TNT, and this is because the explosion method selected for this model is the TNT method. There are 3 methods available and you select between them in the flammable tab section for the model. The TNT method is the simplest, requiring the smallest amount of input data, and is the default method. The report is similar in form to the fireball report, giving the dimensions of the circular effect zones for up to 5 explosion overpressures, where the overpressures are set in the explosion parameters, and also giving the overpressure levels at a series of points downwind from the centre line of the release. The late explosion report gives overpressure effect distance for late explosions occurring at a range of times during the dispersion. For each ignition time, the report gives the location of the cloud centre, the location of the centre of the explosion, the downwind distance to up to 5 overpressure levels, and the flammable mass in the cloud at the time of the explosion. By default, the centre of the explosion is taken as the cloud front to 50% of the LFL, but you can change this setting in the explosion parameters. The two other vessel pipe source models in the Fast example study folder illustrate some of the special model features that are available. The chimney release model models a release of methane from a chimney stack on top of a building, takes into account the effects of the building wake on dispersion. If you view the graphs for the model for all three weathers, and then move to the side view graph, you will see the outline of the building with the chimney on top, and with the three plumes emerging from the chimney. The building wake produces a zone of low pressure, and this pulls the plumes downwards. The model deals with this by adjusting the height at a specific downwind distance, which is 100 meters in this case. In some situations, the plume may be pulled down low enough that all the parts of the plume are entrained in the building wake, but that has not occurred for any of the weathers for this model. The side view graph shows the plumes that never approach closer to the ground than about 58 meters. But if you look at the explosion graph and the flash fire graph, you will see worst case explosion distances of over 900 meters. And flash fire distances of about 600 meters. When performing the modelling of late explosions and flash fires, the program can calculate the flammable footprint of the cloud, either at the cloud centre line or at a specified height. The centre line method is selected by default in the flammable parameters, since this will give the most conservative results, but you should check the side view graph and make a judgment about whether or not the effect zone would actually reach the areas of interest for your analysis. Flash fire in a plume 60 meters in the air would not affect people on the ground, but an explosion in such a plume might well produce significant overpressure at ground level. The long pipeline model models the rupture of a 250 meter propane pipeline that has a pumped flow rate of 10 kilograms per second, where the rupture occurs 100 meters downstream from the plume. The program performs discharge modelling for the complex time-dependent flow regime inside the rupture pipeline, and then performs dispersion modelling for a representative average discharge rate. Select the model and view the graphs for the f1.5 meter per second weather. For this analysis, the discharge calculations are the same for all weather conditions, so you only need to view one weather if you are only interested in the discharge results. The first tab section in the graph window will be the long pipeline tab. This contains a large number of sub-tabs, each of which shows the behaviour of a particular discharge variable against time. Move to the flow rate sub-tab, since this shows the behaviour of the most important variable. The flow rate graph appears to show the flow rate dropping instantly from about 230 kilograms per second to about 10 kilograms per second as shown. However, it is difficult to tell whether or not the drop is instant because the default scale on the time axis goes up to nearly 3,700 seconds. To see the initial behaviour in more detail, you must set the scale yourself. Select Scale and Labels from the right-click menu or on the Graph menu to open the Scale dialog. Then uncheck the automatic scaling and set the maximum time to 60 seconds. And OK the dialog. With the change scale, you can see that the rate takes about 45 seconds to drop to a steady rate of 10 kilograms per second, which is the pump rate. There are 5 lines plotted on the graph, and their meaning may not be immediately obvious. The 2 A lines describe the 100-metre pipe section upstream of the rupture. The 2 B lines describe the 150-metre section downstream of the rupture, and the total line is the sum of the rate released from the 2 sections. The 2 upstream lines show the pump inflow into the section, which is 10 kilograms per second for section A and 0 for section B. And the 2 orifice lines show the flow from that section at the point of rupture. If you want to hide any of these lines, open the plot property dialog and deselect the line in the long pipe tab section. As shown. For the first 9 seconds, the orifice flow rate from both sides are almost identical, as the flash front travels along each section at a similar speed, giving a similar flow regime. However, at 9 seconds, the flash front reaches the end of section A, and from this point onwards, the pressure profile in that section is maintained at the profile produced by a pump flow rate of 10 kilograms per second. The program stops the discharge calculation for section A at this point, which means that there are no results available to display on the graph after 9 seconds, but the 10 kilogram per second flow from section A is added into the total. If you move to the distance sub-tab, you can see that the flash front reaches the end of the section B after 14 seconds. However, the calculations do not stop for section B at this point, and proceed to model the depressurization of the section unit as it empties completely at 45 seconds. If you view the discharge report for the models, you will see that the average rate to represent the behaviour is 10.5 kilograms per second, taken over a timescale of 1 hour. This may underestimate the hazard produced by the release, and there are options available for representing a time-bearing release with more than one release segment, so that you can investigate the significance of the type of short behaviour seen in the release. These options will be described in more detail in the next chapter. The other 8 models in the study folder are not source models. Each models one specific type of behaviour and will produce a fixed set of graphs and reports. Firstly, the warehouse model is a fire in a pesticide warehouse, and you can define multiple scenarios for each warehouse, where each fire scenario is defined by a surface area of the pesticide involved and by the duration of the fire. There are special calculations that determine the release rate and composition for the toxic plume produced by the fire, and the dispersion and effects of the plume are then modelled in the same way as for the toxic cloud for the 4 chlorine models. The 3 flammable models, the pool fire, fireball and jet fire models, perform the same type of radiation modelling as that associated with a source model, but they give you more control over the definition of the flame. They also allow you to specify in more detail the location for which you want to calculate the radiation level. The 4 explosion models, the Baker-Strelo, multi-energy and TNT models, perform the same type of vapor cloud explosion modelling as that associated with a source model, but they give you more control over the definitions of the flammable cloud and of the results location. You've now seen the main features of Phast. When you are ready, you should proceed to chapter 2, which takes you through the stages in setting up your own analysis.